current flowing into the armature of a DC machine produces its own flux, which creates a residual flux density at the interpolar location, so that the coils undergoing commutation, the voltage induced in the coils undergoing commutation is not exactly 0. This creates some problem for commutation, which we will discuss in detail today. The flux density in other places except for the interpolar region can be compensated using compensating winding, but since the compensating winding is a pole facing winding and the pole arcs do not extend really up to the interpolar region, a compensating winding cannot compensate for the armature reaction flux at the interpolar location. For that we need some other arrangements, but first we will find out what are the effects of the armature reaction flux at the interpolar location and what is its effect on the commutation of a DC machine. So, in a DC machine, let us say DC generator. This is the field poles, north pole and south pole. This is the brush position, nominal brush position, the interpolar region, and let us say the machine is rotating in this direction as a generator. These are the armature conductors. The polarity of the currents will be in such a direction which will oppose the rotation. If we take a developed diagram of this, that is cut it open, looks somewhat like this. For simplicity, we have assumed a two pole machine. This is the north pole, this is the south pole. So, these are the armature, one brush is here, the other brush is here. the flux density waveform due to the armature due to the field is trapezoidal. While the armature reaction flux is such that it produces a flux density of the pole left behind. Machine is moving in this direction. So, produces a residual flux density at the brush position, which induces a voltage in the coil undergoing commutation and creates problem with commutation. We will see what kind of problem may arise. For that, let us look at the developed diagram of a armature and the commutator segments. So, these are the commutators. Each commutator connects to two windings. Two coils. So, let us say at any time a brush is in contact with commutator number 1. Carrying a current into it, and the other brush, let us say, is here, one pole pitch apart. Carrying out the same current. So, the brush current enters into the coil, divides into two parts and flows in this manner. Let us say these individual coil currents are IC, this is IC, this is also IC. Therefore, the total brush current entering is 2 IC. Similarly, 2 IC will be flowing out here. it is to be seen that at the position of the brush, the direction of circulation of the current in the coils reverses, and between two brush the the current circulate in the same direction. Now, let us say this commutator segment is moving with a velocity of v c in this direction. So, let us look at what happens when the commutation takes place from commutator number 1 to commutator number 2. So, let us magnify this position. This is commutator number 1 and 2. These are separated by an insulation. Current is entering into the commutator through the brush. Just say this was coil number 1, this is coil number 2. So, at the beginning of the commutation process begins when the leading edge of this brush coincides with the end of the insulation between the two successive commutators. Let us also define a few other quantities. For example, let us say the width of one commutator segment is WC, this is WC, width of commutator segment is WC, width of the mica insulation here is Wm, and width of the brush is Wb. In this particular case, we will assume Wb equal to Wc plus Wm, although it is not necessary. In many cases, brush widths are more. After some time, the position of the commutator of the brushes will be as follows. This is the mica insulation. The brush would have moved connecting both the commutators. this current is still IC. We see that this current is still 2 IC. We see that during this position these two commutator segments are shorted by the brush. This coil 1 is now shorted by the brush. In the beginning the coil current 1 was IC in this direction. This 2 IC divides into this 2 by, let us say, IY and IX. So, we have IX plus IY equal to 2 IC. In the process of commutation, this current will change. The current through this coil, which was IC previously, it will change to minus IC. Let us see how. And at the end of commutation, the commutation process will end when the brush has completely left commutator segment 1, the current flowing still in this direction. This was coil 1, this is coil 2. So, once it has left, this current will now be 2 IC, this current will be IC, and this current will be IC. So, we see if we look at coil current 1, coil 1 current, see in the beginning of the commutation it was IC flowing from left to right. At the end of commutation it still becomes IC, but from right to left. So, in the meantime, during the shorting period the current in coil 1 changes from plus IC to minus IC, and the time taken can be easily calculated by the commutation time Tc equal to, during commutation the brush has moved by an amount Wb minus Wm by Vc. During this period, the current in coil 1 must change from, if we assume this direction to be positive, from plus Ic to minus Ic. Graphically, we can show it in this manner. Let us say this is the instant at which commutation began. At this time, current in coil 1 was plus Ic, and let us say this is the time when commutation ends, this time being Tc, commutation time. During this period, the current changes to, at this instant current changes to minus Ic. The question remains how the current change here. Ideally, we would like the current to change linearly at a constant rate from plus Ic to minus Ic. This is called the ideal commutation characteristics, but in practice it is never so. There are several reasons for this. In some cases, even when commutator segment 1, commutator segment, the brush segment has left commutator segment 1, has moved to commutator segment 2, the current has not fully reversed, but it has reversed only partially. So, maybe it has reached a value of minus Ic dash. If that is the case, then when the contact with commutator segment 1 breaks at the end of commutation, then there will be a sparking. The amount of sparking current will be this. This is called under commutation, that is, the commutation has not completed before the brush has moved from one commutator segment to the next commutator segment. Now, this is not desirable, since the sparking destroys the commutator surface, may also lead to fire hazard. So, this has to be minimized. But let us first find out what are the reasons for under commutation. First is the self inductance of the coil. We see that the current changes from, in time Tc, the current changes from plus Ic to minus Ic. So, net change in current is 2 Ic. Now, the coil undergoing commutation has some leakage inductance. This is mostly due to the overhang part of each coil. So, a coil will have a leakage inductance of Lc. So, this leakage inductance will delay the change in current in the coil undergoing commutation. Not only the leakage inductance of the coil, due to armature reaction, we have seen that the armature reaction flux leaves a residual flux at the interpolar axis, which is of the same polarity as the pole left behind in the generating mode. So, there will be a voltage induced in the coil undergoing commutation, which will prevent or delay the change in the current in the coil undergoing commutation, leading to under commutation. As we have said that the effect of under commutation is to produce spark, this is to be avoided. There are several ways of mitigating the effect of under commutation. One is to use additional resistance in the form of brush contact resistance in the coil undergoing commutation. Let us see, if the brush resistance or along with the contact resistance is large enough, then the time constant formed by the leakage inductance of the coil and the brush contact resistance may be small, which will hasten the change in coil undergoing commutation and will reduce spark. This is with brush resistance. This is called resistance commutation, but this cannot completely eliminate the sparking. For that, it is necessary that we neutralize the residual flux at the interpolar region. There are different ways of doing it. One is the so called giving a brush lead. If instead of putting the brush actually at the interpolar region, if we shift it or lead it, that is move it in the direction of rotation in the generating mode, what will happen is that in the process of rotation, the induced voltage in the coils will change to the polarity of the pole ahead before it reaches the brush. So, there will be a voltage induced in the coil undergoing commutation, which will assist or hasten the change in current in the coil undergoing commutation. So, this can mitigate to some extent the problem of under commutation. However, as we have seen earlier, that giving a brush lead creates a demagnetizing MMF along the direct axis, that is the pole axis, because once you have shifted the brushes, the polarity of the currents will change, and if you have given a brush lead of beta, then the conductors between the angle 2 beta will produce a demagnetizing flux, which will tend to reduce the main flux. This is called the demagnetizing ampere turns. And it is directly proportional to the brush shift given. So, although giving a shift to the brush, lead to the brush may help commutation, it will have a demagnetizing effect on the main flux, which can be of course compensated by increasing the ampere turns on the main flux. Another approach of providing additional ampere turns is by providing what we call the interpoles. The interpoles are short poles provided between two main poles. So, these are the main poles, let us say. This is the armature. These are the brushes. The main flux out of this flows in this direction. This is the main flux. Let us say in the generating mode, the direction of rotation is this. In which case, if we take two armature conductors, the polarity of the currents will be this dot, this cross, in which case in the generating mode the MMF produced by the armature coils, because these are all cross here, and all dots here, So, the armature MMF produced the armature flux armature reaction flux will tend to flow in this direction In other words, the armature MMF will produce a virtual north pole at the interpolar region, a flux that is equivalent to a north pole, that is the pole left behind in the generating mode. So, if we want to cancel this flux, then in the interpolar region we can put an actual south pole, that is this south pole, and a north pole here. So that the flux produced by this north pole will cancel the armature reaction. Not only it will cancel the armature reaction flux, but it will also produce a flux which will generate a voltage in the coil undergoing commutation of the polarity in the that it will have under the pole ahead in the generating mode, which will assist commutation. So, these are called interpoles. Interpoles are short and narrow pole structures placed at the interpolar location in order to compensate the interpolar armature reaction flux. And since the interpole is supposed to compensate the armature reaction flux, these are excited by the armature current, that is it should the interpoles are excited by the armature current, that is the coil on the interpole is connected in series with the armature winding, so that at all load conditions it can cancel the armature reaction flux. Now, let us see how much this flux density at the interpolar region is required. The voltage induced in the coil at the interpolar location will be 2 times the interpolar flux density, desired interpolar flux density Bi into length of the conductor into velocity of the armature
into number of turns, this should cancel the voltage due to the self inductance of the coil undergoing commutation. So, ideally what we should have is that the interpoles will not only compensate the armature reaction ampere turns, but in addition it should also generate a flux density at the interpolar location such that the voltage induced due to the in the coil undergoing commutation due to that flux density cancels the voltage induced by the leakage inductance of the coil undergoing commutation. However, there is a practical difficulty because finding out the value of the leakage inductance is not easy, and this flux density has to be set by somewhat a trial and error method. Once we have find out the required flux density Bi, then the required ampere turns for the interpole can be calculated as follows. Ampere turns of the interpole should be equal to peak armature reaction ampere turns plus the ampere turns required to generate a flux density of Bi at the interpole. Since if we neglect the ampere turns required to circulate flux in the core, this is given by where Bi is the flux density, required flux density at the interpole of the desired polarity, mu 0 is the permeability, Lg is the length of air gap at the interpole, total length of air gap at the interpole, and of course mu naught is the permeability of the free space. Now, peak ampere turn we know per pole is given by equal to, if the armature current is IA, then the current in each parallel path is IA by A. If there are Z number of conductors, then turns per pole is Z by 2P. So, the peak ampere turns is given by IA Z by 2 A P. So, from which we will be able to calculate the required ampere turns of the interpoles and the corresponding number of turns in the interpoles. So, let us try to solve some problems involving the commutation and induced voltage, interpoles, etc. of a DC machine. Let us say that we have a DC machine with 8 poles there are 960, that is P equal to 8, there are 960 conductors, that is Z equal to 960, which are lap connected, The flux per pole of the machine is 40 milliweber. If we want a no load induced voltage E of 256 volts, what should be the speed of rotation? This is a straightforward application of the formula of induced voltage, which is given by E equal to phi p into Z n p by 60 A, where phi p is the flux per pole, Z is the total number of conductor, n is the speed of rotation in rpm, p is the number of poles, and A is the number of parallel paths. In other words, n can be written as 60 E A divided by phi p Z p. In the given problem, p equal to 8, Z equal to 960, phi p equal to 40 into 10 to the power minus 3, and since the machine is armature is lap connected, A is equal to P equal to 8. Therefore, the answer will be n equal to, substituting all these values, we get n equal to 400 rpm. It will be interesting to find out, if I run the machine at same 400 rpm, but change the armature conductor connection to wave, what will be the induced voltage? We know for wave connection, A equal to always 2. So, for wave, E wave will be equal to phi p Z n p by 60 A. Substituting the values, phi p equal to 40 into 10 to the power minus 3, Z equal to 960, A equal to 2, P equal to 8, we get E wave equal to 1024 volts. So, the induced voltage in a wave connected machine at the same speed will be much higher. Now, let us look at the problem of commutation. Let us say that we have a machine with 4 pole which carries a full load armature current IA of 143 amperes. There are total 492 wave connected conductors. In order to mitigate the commutation problem, a phase lead beta of 10 degrees is applied to the brushes. What will be the demagnetizing ampere turns? we have seen in our previous class that armature reaction flux AT peak is given by IA by A, which is the coil current, into Z by 2P. If we look at the picture, let us say this is the nominal magnetic neutral axis. If I give a phase lead of the brushes of beta, we have seen earlier that all the conductors inside the angle 2 beta produces demagnetizing ampere turns. So, the demagnetizing ampere turns demag AT will be equal to AT peak beta and is the 2 beta is the angle over which the conductors will demagnetize, and between two poles the separation is 2 pi by P. So, demagnetizing AT will be Z IA by A into 2 P into beta P by pi, or this will be equal to Z IA beta by 2 pi A. Substituting the given values, A is the number of parallel paths, and in this case A equal to 2. Substituting the values, we get demagnetizing AT demagnetizing equal to 1011. If the field current is known, then we can find out the number of extra turns that will be required on the field winding in order to cancel this demagnetizing AT. So, this divided by field current will give you the number of extra field turn required for this machine.